This is a part 4 of the introduction to the divergence in Stoke's theorem, and I mentioned this in the third part of the video, but I'd like to go a little bit more detail since it's not that complicated. So here again, the main issue here, or the theme, is about these two collections of vector fields with a curl 0 and the collection of gradient vector fields. And these two things becomes exactly the same when the region is something called simply connected, and if not, there's sometimes these two things are not the same. So we've seen that example. So we're gonna take this into a more three-dimensional situation, and the surface is in three-dimensional space. So comparing these two things, looking at more examples, is what this video is about. So this is one of the examples we looked at as the first one, where there is a vector field that is defined nicely on this donut shape in xy plane, and it has a curl 0, but it cannot be realized as a gradient of a scalar function that is defined on this donut shape, which is summarized in this sentence here. So there is this vector field with the two components, with a curl here, it's a 0. In this case here, the curl is just qx minus py. And all the gradient vector field has this property that if you take the qx minus py by Clairaut's theorem, it's a 0, but there is a vector field that is all well defined around this region, but it cannot be realized as a gradient vector field. So this was an example, and I explained in class probably that this type of example arises from complex function, complex numbers, but if you just focus on it here, that's a vector field with the same scalar. So negative y comma x is kind of the direction, and it's kind of scaled. If you look at the magnitude of this vector, without the scalar x squared plus y squared, then the length of this vector is going to be x squared plus y squared again, so we're dividing by its own length, so this is a unit vector. Now, because the curl here is a 0, if you actually calculate the curl, it turns out to be the 0, you can actually do this integral. You can take this function and try to integrate with respect to x, and by doing that effort, you'll be able to find actually the gradient, the scalar function whose gradient is equal to the given vector field, just locally, just around that starting point. For example, and you can see this vector field has a problem at 0, 0, that's this point, and if you start from any point in here, integrating with respect to x means you're kind of dealing with this horizontal line with respect to x, and you have to move around the x-axis. So if you happen to be on the negative axis or positive axis here, when you move along and you bump into the 0, 0, so that's a problem. So if your y-coordinate is not 0, then if you're somewhere in here, if you integrate it, and you will have no problem with actually finding the antiderivative of this one with respect to x. So if you do this trig substitution method, it turns out it's negative tangent inverse x over y. If you actually differentiate this one, you can verify that this is exactly so. But this is only valid for when y is greater than 0, less than 0, when y is not equal to 0. So again, we didn't find gradient vector field that is defined everywhere. We just found one that works for the upper half of the donut shape. So here's a picture of what's happening around y equals 0. We don't want to go close to 0, 0. This is not even defined, but if you have a point on this positive x-axis, such the y-coordinate is 0, if you approach that point from above, staying on the upper half plane, if you look at it here, x-coordinate is a positive, and y-coordinate remain positive but very close to 0, so that blows up to positive infinity, and we know, so I missed the negative, I put it in there, so positive, and there is negative outside, so this approaches negative pi over 2. But if you approach from below, x is still positive and y is kind of a 0 minus, so this whole thing will be negative infinity, so that goes to negative pi over 2, so together that becomes a positive pi over 2. So that's the behavior. So it is interesting, it doesn't matter what an x value is here, it's always approaching negative pi over 2 and always approaching positive pi over 2. So remember, when you compute the antiderivative, you can always add some constants, and you still have the same property, that derivative property. So we can kind of add some constant to here and there to make this one kind of connected. Then we call it analytically continued. This differentiable function is nicely connected through this positive axis of x-axis. So if we add we can use the same formula for y less than 0, but if you add negative pi, you can see that takes these two constants exactly the same if you add a negative pi in there. So they're nicely connected with this constant. So at least for that part, the positive real the x-axis, we have connected these two functions nicely and differentiable and continuous. So if you go back to this picture we took care of, we found the scalar function whose gradient is exactly the given vector field from here to there. We're just missing just this part, and see what happened along that part in here. So which was summarized in this picture. So we have a great scalar vector, scalar function nicely defined in here, whose gradient is this given vector field. Let's see what happened over the negative x-axis. So I have to fix this one, I messed up earlier. So I just fixed it. So that was second quadrant over here. So x is negative and y is remaining positive. So altogether it's going to be a positive sign. So it's positive infinity. It's going to positive pi over 2. Down here is an x and y both negative, so they're going to negative pi over 2. But there's negative pi we added there, so altogether is negative 3 pi over 2. So here's the situation. So we continued it, and you can see that down here, negative x is these two values not equal to each other. So there's no way you can close up. We have this solid function defined all the way in here, and it is not closing up. These two values are different. So we fail to continue this scalar function all the way around. So let me explain what this one's showing. Later, actually, to argue that there's no gradient vector field that is equal to its vector field capital F, which is given earlier, we actually will do the line integral around this problem point 0, 0 and show that's not 0. If there is a gradient vector field, then by the fundamental theorem for a line integral, that has to come out as 0 because it's simply fb minus fa, and if there is the gradient vector field and these two points, the value will be exactly the same. But we do have gradient vector field right up to that point. So if you just calculate this line integral of the vector field f, capital F, just very close to a comma b, and it is true because this line integral is going to have a limit. If we compute the limit of this type of line integral, that's going to be the same as just full line integral of this vector field, because this vector field is defined around this part. Only this point is not defined. And again, when you try to find the potential function, the problem is not just this point. It turns out this entire line is a problem, so that we cannot use a fundamental theorem of line integral, but we can still do this in the integral. It's okay. So if you use this one to kind of approximate this one, then we can use this fb minus fa, which is still fundamental theorem of line integral, because if this entire loop circle remains in this part here, and we can use a fundamental theorem of line integral. So you can see this approximately equal to this value, and this should be approximate, not equal. Sorry about the mistake. And it is approximately 2 pi as we go around from here to there, because that discrepancy here is becoming the 2 pi. Another way to seeing this phenomenon is go back to this actual formula and really directly compute this one. So we wanted to determine that we were claiming that vector field is not the gradient vector field defined on this entire region except 0, 0. If so, again by a fundamental theorem of line integral, this line integral should turn out to be 0 because this is just fb minus fa, and then these 2 points are the same. But if you actually plug those into the formula of the vector field, let me show you the vector field. So this was the vector field, and if you just do this integral around the circle, this integral behaves nicely because x squared plus y squared in the denominator. And it's not hard to compute. This one actually turned out to be 2 pi. So it's an indication that it's not at 0, so it contradicts this fact if you assume this vector field is a gradient vector field. And this is the part that I had in here. It's just the picture just to visualize what kind of vector field it is. Again, if you look at the numerator part, it's just negative y comma x. That's a perpendicular vector. This is position vector 0, 0 to x comma y. So that's this way of the direction. But if you have the scalar x squared plus y squared, that turns this one into a unit vector. So it has to be perpendicular to this line segment to the origin and had to have a length 1. So everywhere you choose a point is going to have a unit velocity vector or vector field. So that's kind of clearly visualize what kind of vector field we're looking at. One of the main topics in the next part is this vector field on a surface in an XYZ space. Okay, so we're actually looking at what we mean by this. I'm going to explain the meaning of this one. And this vector field is actually defined not only on a surface, but slightly more than a surface, and that's the meaning. And we're going to examine then curls and the gradient vector fields over these guys. So at this stage in the calculus 3 level, it's not easy to define the vector field just defined on here. It's an easy way to think about it is a vector field that is actually defined an entire XYZ space, and then we just restrict those points down to here. That's one way to think about it. And another way is that is the following. So here I'm pointing at the thin slide. The vector field has these 3 components P, Q, R sitting inside this 3-dimensional space. That to get the idea about the differentiable on this R happened to be just the surface. And we have 3 components, and we have a 3 variable if you want to look at this as a function with x, y, z in it. And it is difficult to think about what this meaning of the differentiability on R. So we're going to introduce this slick notion is the following. We're going to say this PQR, these are the scalar component here, are differentiable on this surface R. If there's you can thicken this one just around the neighborhood to create this nice little bit of a solid in there. And in that way we have a 3-dimensional space around this R. The meaning of differentiability on that solid makes sense. But again, what I'm trying to do here is make sense out of the differentiability in 3-dimensional space, and we're restricting ourselves onto this surface. So again, the resolution is that we're going to make it a little bit thicker, then turn it into a thin solid, and then we have the 3-dimensional space. So differentiability requires all directions in 3 x, y, z directions, so that is possible here to think about it. So that's the meaning of differentiable on R. It's not the way the modern mathematicians define that differentiability, but I think that that's going to serve the purpose for this video and the calculus 3 level. Okay, so again the question is that, okay, we have now thin solid here, and we have all the vector fields, and of course we're looking at the vector field with the curl f equals 0, just like the earlier case. And the gradient vector field that is defined on this thin solid, and their curl is 0, so we know the gradient vector field is in the pool, the collection of the vector field with that property. And then we're again asking the question that can there be a vector field in here and whose curl is 0, but it is not the gradient vector field. And we're going to look at some examples. So this is one of the examples that was introduced in an earlier video, and I think it was introduction part 3, and I'd like to give a concrete example. So we're going to have this torus. So that's not a solid, it's just the surface of this torus. This is a donut shape, an actual donut shape, and we're not including inside or this part of the inside or anything, just the surface part. And I'd like to think about the vector field that is defined on that. Again, the meaning is that you have to turn this one into a actually thin solid all around. You have to introduce that. And then we have differentiability, the meaning of the differentiability. So we have vector field in that sense. And the claim is that there is a vector field F on this R, meaning that is a thin solid E with a curl 0, but it is not going to be a gradient vector field. Example turns out to be exactly the same example we looked at in detail. That's why we looked at it in the detail, to understand this phenomenon a lot better. Only difference is that we're lifting this vector field into three-dimensional vector field. So it is really like a parallel to xy plane and not really moving anywhere, and then completely disregarding the z component. So this vector field is just happening everywhere, whatever that was happening in xy plane. Alright, here's the picture. I slide up a little bit. So that's the vector field, and that's the xy plane. I don't know why I slanted, but it's supposed to be upright, if that helps. So that's a z-axis, and that's the xy plane. We sketched that vector field before, so that's going around like this, and that's what that vector field is. And what is happening at z equals 1, this is where z equals 0, z equals 1, and exactly the same copying up and down. So that's the vector field we're looking at. To see this is not a gradient vector field, we have to find in the three-dimensional space, we have to find a loop such that if you do the integral, the line integral of that loop, it doesn't turn out to be 0, just like before. If it is a gradient vector field like this, by fundamental theorem of line integral, fp minus fa, if it's a closed loop, has to be 0. So we're going to go into this donut shape and find a loop in here, and such that its integral is not 0. It turns out you can choose just any curve in here that it's kind of parallel to the xy plane. It doesn't matter if it's parallel or not, but it's easier to compute. So you're going to take this curve, here's x and y, xt and yt, that's a little loop in here, and z is constant. It could be z, k can be 0. Then if you go through this line integral against this one, you can see dz dt is going to be 0. So when you dot it with this one, we're actually doing exactly the same computation we did for xy plane. So this is x component, y component, and dx dt and dy dt multiplied there. That's exactly what we're doing with that xy plane. So we know it's going to turn out 2 pi, like this. So therefore, there's this loop, and line integral of this one around that loop is not 0, and it's a closed curve. Therefore, this single example defies the existence of the potential function whose gradient is this given vector field. And this line here, this time is serving as a z-axis, but this is where this vector field is not defined. For example, if you look at x squared plus y squared in the denominator, and they can be 0 only when x and y are both 0, and there's no condition on z. So everywhere 0, 0, any z value will give you a problem of this one being defined. So that's why it's happening. Suppose there's some weird formula so that it doesn't extend to the infinity, it kind of stops right there and right there. So there's this finite length of points in this xyz space such that the vector space is not defined. Then you can actually go around and close the loop, and then you can move around, and it turns out it has to be 0. So it is very, very interesting to the way the formula looks like that, and then it kind of defines where these vector field is defined, kind of shapes it. And in this time we're missing this entire kind of infinite line as causing a problem with this loop. So that makes this thing is non-zero like this. So example was already there, and it is easy to kind of lift this one up to this its important example in mathematics and geometry. Again, it's kind of this shape, kind of number of holes is kind of realized by this singularity, so-called, of this vector field, and we see this thing is happening in front of our eyes, but these differences between the collection of these type of a curl, this type of vector fields and gradient vector field, and they try to measure the differences, and then kind of this kind of a number of holes in the shape kind of reflected in how big they're and how much they're different and so on. So they're all nicely quantized in the higher mathematics, and this became important topics in algebraic topology later on. So this is the important beginning of something called algebraic topology. Next example is the same old sphere. The standard notation for this one is S2 and sitting inside three-dimensional space. Again, we're going to look at all the vector fields that are defined on S2. Again, what we mean by that is you have to think about this thin solid that surrounds this sphere, and think about all the vector fields and with the curl 0. And this time, turns out on all the vector field with the curl 0 is exactly coming from some gradient vector field. So what's the difference between this one and that one? It's that kind of hole that this line can go through, right? To better understand this, we have to look at this two-dimensional case, and here's again this xy plane. Suppose we happen to have a vector field not in three-dimensional space, in two-dimensional space here. We have no problem with that, it's well defined. And suppose that vector field is well defined in this region D, so-called simply connected. So right out here, the simply connected, the meaning of the simply connected again is if you have any loop inside this region D, it can contract continuously remaining inside this region D, and can contract down to a point. So if you have some sort of C in there, that means inside the C here region, this vector field we started with a PQ component is well defined in here. So that's the meaning of simply connected. Think about the very first example to look at is a donut shape in the xy plane. Then if the function is not defined at the center of that missing part, you cannot create this type of closed region. So I moved up so that I can show what's written here, just so that we can close up this curve C inside. Okay, if we have a curve C and then all the thing that's kind of inside in this simple situation, and the vector field must be well defined in that region C. Okay, that's the use of this simply connectedness. So if we have that, so what that gives us is this f of the vector field is nicely defined everywhere, and whatever loop you have in there inside is going to close up like this, and this f is defined. Now because this vector field is defined all inside, then we can use the Green's theorem. This line integral around the C can be written as a double integral, which requires all the inside things defined. That's where we use it, and it becomes this double integral of this curl. And because we defined the curl as 0, this is going to be 0, so the whole integral is 0. So it doesn't matter what curve you choose, this region close up, and by Green's theorem is going to be always 0. So all the closed over the closed curve, this line integral is 0. That's called path independence. Remember, what we mean by the path independence is integral going from this point to that point in a different route, and the value is going to be always the same. It's because these two different routes actually makes a one closed curve, and if you separate it and change the orientation, this line integral being 0, it's equivalent to these two different paths at the same integral value. So that's what we mean by path independence. And we have this, once we have this path independence, we use that path independence to define the potential function, which is going to be the gradient vector field, which is defined this way. You have to start with the sum point in here based on that some point a comma b, and define the function value, the scalar function, to be the value of this line integral from here to there. and then it doesn't matter how you get there because of the independency, and this is going to define well-defined function. So if you do the derivative property, and then you can check that this has the partial derivative p and partial derivative q. So that's realized this capital F as a gradient vector field. So that was the outline. Think about where the simply connectedness kicks in is that when you pass from the line integral to the surface double integral, it requires this vector field is defined anything that is inside closed up by this curve C, and that's where we use it. Right, so for the proof of the sphere case, we start from the solid construction. So E is going to be the solid that slightly thickens this S2. The vector field, so we're talking about is vector field defined in that three-dimensional space solid. And as importantly, we would like to recognize is simply connected. Okay, so let me explain that about a little bit. So this is how we're going to use the simply connected component, the property. Suppose the C is inside that sphere, not actually the inside is on the sphere, that's what I meant, and this live inside this actual solid. And if we can close up, so we can close up into where these vector fields are all defined a bit inside, and then we can use the Green's theorem, or in this version here is a Stoke's theorem. So the fact that we can, anytime we have a curve on the sphere, we can close up using the parts of the sphere that all the vector field is defined on any part of this surface, which is actually can be the part of the sphere or very close to the part of the sphere because we're in this thin solid. So this is always possible if you think about the shape. And it is really coming from the property that simply connectedness. Any loop can contract it to a point when you contract it, and it kind of creates the families of the curve, right? And that actually generates the surface as we shrink it inside. So that's where we use the simply connectedness. Again, start from the curve, and we can construct this surface that has this boundary C, such that the vector field, given vector field, is defined on the C. Whenever we have this situation, we can use a Stoke's theorem. And of course, the Stoke's theorem says if you have a line integral, we can turn this into a surface integral where the vector field is a curl, and our assumption is that we're having this vector field where the curl is 0. Therefore, this whole thing is going to be 0, like this. Like the Green's theorem case, this exactly applies a path independence. If you want to go from one place to another in a different path, and it's let me show you the picture. It was here before. You can just lift this one to three-dimensional space. Suppose this is actually happening on that sphere S, and this makes a closed curve, so you can separate it and changing the sign. Then we can create a two different path. Since the integral is 0, this creates a path independence. Like we did for the Green's theorem, once we have a path independence, we can define a function from one point to another by just evaluating this integral. It doesn't matter how you go from here to there, this value is going to be always the same, so we can define that as a three-dimensional scalar function. Again, all these things happening actually not on the surface S2, but on that thin solid E. So here showing on the picture, wherever you are, so for example, some sample points on the sphere, and this E is the solid. There's this slight thickness in there, and remaining inside there, you can go from here to there any way you want. And if you zoom in to this XYZ plane, then you have this three-dimensional space, although it's tiny, that's just enough to calculate the partial derivative of this one, x and y and z. And if you just follow through, and it is the case that the partial of this one, x, y, and z is exactly PQR component of this vector field. So again, let me emphasize one more time, the simply connectedness realized not on the plane situation, but on the surface of it's sitting inside three-dimensional space, and it can be still simply connected, and whenever that happens, and the Stoke's theorem allows us to realize this vector field with the curl 0 as a gradient vector field. Back then, when people were thinking about this type of property of the shape, then it was Poincaré who had set out the conjecture, his famous conjecture about the simply connectedness in a higher dimensional space. I want you to go and read about in the internet. It's a wonderful history in mathematics.